All right, folks, this video is going to teach you how to calculate the center of mass of what I call blobs or point particles. Okay, so up to now, when we said, where is whatever object it was that we were studying, we didn't really pay attention to, objects take up space, so that was kind of confusing. Usually it was understood, oh, we care about where the front of the fan card is or where the back of the fan card is. But technically, we need to be a little bit more specific. And most of the time, physicists are talking about when they say where is something and we don't specify the front or the back, then it's understood that we're talking about the center of mass. So we need to know what that means. So technically, the center of mass is a weighted average of where the mass is. And note that it is a mean, not a median. So there's no guarantee that if you slice something through the center of mass, that half the mass is above and half the mass is below that point. I think the reason we think that is because if something's symmetric, then that is the case. Okay, so let's talk about what a weighted average is. So what we have here is, just made up some numbers. For some weird reason, 3 people got a 94 on a test, 1 person got a 91, 5 people got an 88, and 2 people got an 83. So if you wanted to calculate the average, the traditional way, you would add 3 94s, a single 91, 5 88s, 2 83s, and divide by the total number of tests, which would be 11. If we wanted to be lazy, clever, and attractive, we could calculate what's called a weighted average. So we would weight the score of 94 by 3, because there were 3 of them. We would weight 91 by 1. We would weight 88 by 5 and 83 by 2. And we'd still divide by 11, and the average is 89. Okay, so that is an example that I thought would make sense to you all. All right, so let's see how that applies to mass. We're going to, we can only calculate the center of mass of what I call blobs, which is a little bit artificial, but on some level, you could use this if you were if you were a chemist and you wanted to find, say, the center of mass of a water molecule. Most of the mass is in the nuclei. So the nuclei are essentially blobs of mass at specific points. Okay, and if you, when molecules will rotate back and forth because they have some energy, they were hit by another molecule, they're going to rotate about their center of mass. So I know this might seem weird because you're like, well, most things in life, aren't composed of gumballs connected. But again, part of this point is because we don't want to have to use calculus to calculate the center of mass, because you have to use integration, and we're not ready to do that yet. So we're just going to find the center mass of blobs. It's going to come into play when we talk about collisions, and you have, again, it seems kind of artificial, but you'll have blobs of mass like a dumbbell, and then something else will come along and collide with it, and it will rotate about its center of mass. Okay, so the formula, which is given on the AP formula sheet, and I will give it on a test if you need it, is the center of mass. This is a 2-dimensional picture, so it's going to have an X coordinate and a Y coordinate. Okay, so what we have here is 3 blobs. We're going to do the problem on the next page. I scanned this in from your textbook. The size of each red gumball represents how much mass there is. And then this little tiny dot here is actually the center of mass. there isn't actually anything at that point. Okay, but you can see that that location you have to go over and up to get to the center of mass. Okay, so hopefully you can see the connection between this formula and what we had on the previous page. Each of these blobs is at a specific coordinate, which you'll see on the next page. And each of these coordinates is going to be weighted by how much mass is there. So for example, M3 is 3.4 kilograms and M2 is 2.5 kilograms. So M3 is going to shift the center of mass up, and M2 is going to shift the center of mass to the right and down. Okay, and then you are going to calculate on average where is the mass. And then you'll do the same thing for the y coordinate. All right, so here is the information. You have 3 blobs of mass. You are told how much mass each object is. Again, these could represent the nuclei of a molecule. And you have the x and y coordinates of each blob. All right, so to find the x coordinate of the center of mass, we're going to weight each coordinate x by how much mass is there. So the mass is kind of like how many tests there were. So 1.2 people got a 0 on a test. I know that doesn't make any sense, but and 2.5 people got 140 on a test, and 3.4 people got a 70. Okay, and then we're going to divide by all of the mass. Okay, so what we have is, and this is in centimeters, yeah. So we have 1.2 kilograms with the location 0 centimeters weighted by 1.2 kilograms. And then we have the location 140 centimeters weighted by 2.5 kilograms. And then we have the location 70 kilograms, because we're just doing the over, weighted by 3.4 kilograms. That coordinate counts the most. And then when we divide by the total number of kilograms, which is 7.1. Okay, and then this is 0, which sometimes people are like, why are you doing that? But you can think of this as shifting the center of mass closer to the origin. Plus 350, I'm going to put the units in so you can see what happens, 350 kilogram meters, plus 238 kilogram meters, and we're going to divide all of that by 7.1 kilograms. And this turns into 588 kilogram meters over 7.1 kilograms, and you can see that the kilograms cancel, and we end up with 82.8. Oops, sorry, these aren't meters, these are centimeters. Apologize, I think you can figure that out. These were centimeters. Okay, so they did make this diagram to scale. The x coordinate of the center of mass is 82.8 centimeters. All right, and then you're going to do the same thing for the y coordinate. Okay, so same thing for finding the y center of mass. We're going to take the point 0 and weight it by 1.2. We take another 0, weight it by 2.5. So that's just going to shift a whole bunch of stuff. That's going to shift the center of mass down. But we're going to weight the 121 by 3.4. So that's going to shift it up, which is why it doesn't end up so close to the x-axis, because M3 is so massive. Okay, and again, don't forget to divide by the total mass because it's an average, and the kilograms cancel, and the vertical location of center mass is 57.94. Okay, that's what you're going to need to do for the gummy bear lab, and for calculating the center of mass of dumbbells for collisions that cause rotation. A couple more things. Sometimes on the AP, very, very occasionally, but sometimes they will give you a solid object and you have to integrate to find the center of mass. And it just, to me, is not worth spending 2 or 3 days to have it make sense, because what you're doing is you're looking at every single coordinate weighted by a little bit of mass, dm, and then you have to figure out how to convert a little bit of mass to position. It's very abstract. It's cool. It's very abstract, but to me, it's not worth it, because it's not a heavy emphasis on the AP. And they almost always say, you know, show that the center of mass is such and such a location. And you could always kind of punt. But my point is, for everybody, that in real life, things are not blobs of molecules at specific points. They take up space. You have to add up every little bit of mass, right? And that's why you need calculus. So it's very cool. It's a really neat application of integration, but we're not going to talk about that in this class. But clearly, so if the object is solid, meaning not blobs, you must use calculus. But you know that if it has symmetry, the center of mass lies along that line of symmetry. I think I scanned this in from your textbook, and what's kind of cool is you can see that the cone is shifting more mass to the floor, and so that's going to lower the center of mass. All right, just like there's no one single person necessarily who had a grade, the grade on the test example, that was equal to the average, there may not be mass at the center of mass. All right, so there used to be a website where you could put blobs down and it would show you where the center of mass was. So clearly I did not make a perfect circle here, but if you sliced half of that mass and only had half of that circle, in theory, the center of mass should have been on, you know, the line of symmetry, but that's going to shift the center of mass way up, right? Because you removed all the mass that was on this half of the circle. Okay. And we already did that. Like, clearly, if there's symmetry, you know where the center of mass is. All right, so that's the foundation of calculating center of mass. So hopefully that makes sense, and thanks for listening.